Hey gang, welcome back to another video on thermodynamics. In today's video, we're going to talk about the ideal gas law. We're going to introduce the concept of equations of state, and then we're going to talk about some relationships that pop up between enthalpy and internal energy for an ideal gas. So you've seen in high school chemistry an ideal gas, you've heard about it, and you know that it's an ideal gas is a hypothetical gas where molecules have no intermolecular interactions and they have no volume. And we have the ideal gas law that goes along with it, which is PV equals nRT. Now, we have spoken about that in a previous video. You have intensive and extensive properties. And what we can do is we can actually change some of our extensive properties into intensive properties with the ideal gas law. So if we take our moles and we divide it to the left side, we have P V over N equals RT. And that V over N can then become our V bar, our specific molar volume. And this is just a different form of our ideal gas law, but it can be really handy because now all we have are intensive properties. And when we deal with the ideal gas law, something I just want to remind you about is that you need to make sure you're dealing with temperature on an absolute scale. Usually we're going to deal with Kelvin, but in rare situations, maybe you're going to use Rankine. Now, with the ideal gas law, as we've talked about, there's several characteristics that go with an ideal gas. So the first one is that gas molecules have zero volume. The second one is that the particles in an ideal gas are in constant motion. Collisions are perfectly elastic. All the energy is retained when the particles collide and they keep bouncing around in your container. And the third one is that there are no intermolecular attractions or repulsions. Now, obviously that's not always going to be the case. And when we do have that, that's going to be under situations where you have a low pressure and high temperature. That's when we can assume we have an ideal gas. Now, in situations where you do not have low pressure and high temperature, obviously we're going to deviate from having an ideal gas, and that's where we now can use equations of state. So those are relationships that relate temperature, pressure, and molar volume. So if we start with the ideal gas, P V bar equals RT, right? This is assuming a bunch of principles for having an ideal gas. And what we're going to do is we're going to modify this a little bit to correct for some of those assumptions. One of the first equations of state that came up is the van der Waals equation of state that started to correct for different parts of your ideal gas equation. And the van der Waals equation is the one I'm showing on the screen where it's P equals RT over V bar minus B minus A over V bar squared. And so I want to talk about those two terms, B and A. So B is a correction parameter that accounts for the volume of the particles. And as you look at the denominator, our B is going to have units of specific molar volume so that it works out with my V bar. The other term, A, is a parameter that accounts for the effect of intermolecular attractions on pressure. And with the van der Waals equation, there are ways that you would calculate A and B. We're not going to get into that in this video, but I want you to know that you can calculate those with several different equations for the van der Waals equation. The other equation of state that we can talk about, or another factor we can talk about, is the compressibility factor. And with the compressibility factor, what it's doing is it's just combining all our terms, our pressure, V bar, and temperature together on one side. And that gives us our compressibility factor. If you have an ideal gas, your Z value, which is our compressibility factor, is going to actually equal 1. Now, the other cool thing is you can rewrite your compressibility factor equation to look similar to an ideal gas equation where it's P V bar equals ZRT. Now, with the compressibility factor, the other unique feature of it is that you can use that in line with the law of corresponding states, and you can actually extract some different relationships and do some predicting on the properties of your real gas using the compressibility factor. but that's going to require you to use some compressibility charts and do some additional calculations and use some relationships to do those predictions. Again, we're not going to get into that in this video, but I want you to know that that exists. Now, going back to ideal gases, I mentioned that there's some relationships that develop with internal energy and enthalpy. Now, we know that enthalpy is equal to U plus PV. And we just talked about the ideal gas law where it's PV bar equals RT. You notice how PV bar equals RT, we can actually substitute that RT term into my enthalpy equation. And now I can, for an ideal gas, say enthalpy is equal to U bar plus RT, which is, again, only true for an ideal gas. The other relationship that comes up is one that relates our constant volume and constant pressure heat capacities together. So in this case, if we look at our constant volume heat capacity, it's equal to the partial derivative of our specific internal energy with respect to temperature at a constant molar volume. Now, we can rearrange that and it eventually becomes du bar equals CV star dt. Now, I will admit that there are some behind the scenes math that allows us to simplify our partial derivatives into a normal derivative. That math hinges on the fact that ideal gases do not have any changes in volume. They actually have no volume. And that allows us to make this simplification from a partial to a normal derivative. Now, we can also write this equation, or we can write something analogous for our internal energy for enthalpy, where dH bar is equal to Cp star dt. And something I want to make a note of is that your stars are a notation to indicate that you are dealing with ideal gases. So Cv star, Cp star, those are specifically for ideal gases. And so now that we've got something for our we got something for internal energy, we have something for enthalpy, what we're going to do is we're going to try and relate our Cv star and Cp star together. Now, for enthalpy, we know that it's equal to U bar plus PV bar. And so what we'll do is we're going to substitute in that U bar plus PV bar for our enthalpy, constant pressure, heat capacity equation. And from here, as we did earlier, we see that we have a PV bar term. We can use the ideal gas law. We can substitute in RT on the left side. Now that we have that, we can differentiate our two terms on the left side, and that's going to be du bar plus rdt equals Cp star dt. Now, the final piece that we're going to do here is you see that we have du bar. We actually have an expression of Cv star dt, which we can substitute into that equation we have, leading us to Cv star dt plus rdt equals Cp star dt. And as you might notice, you see that there's dt's for each of the terms, and we can cancel all those out. Now, I will make a disclaimer that technically this is not mathematically a legal move, but it does work out, and it's going to be the final outcome is the final outcome that should be happening. We're just jumping a couple steps to get to that outcome by canceling out our dt's. So ultimately, because we cancel out our dt's, we're going to end up with Cv star plus R equals Cp star. And again, this is for ideal gases only, but it's pretty exciting that we're now able to relate our constant volume and constant pressure heat capacities together in this simple equation. And so that's everything I want to talk about in today's video. So to summarize this, we talked about the ideal gas law, we talked about the characteristics of an ideal gas, we talked about van der Waals equation of state and the compressibility factor, and then we talked about some relationships between enthalpy and internal energy and found a way to relate our constant pressure and constant volume heat capacities. So thanks a lot for tuning in, and I'll see you in the next video.